After observers detect edges and group them, they have to orient the grouped elements in a 3D space to form, in David Marr's term, a 2.5D sketch before recognizing them as objects. From a representational standpoint, the retina is 2D, so the retinal image or the proximal stimulus is 2D. To regain the third dimension, to approximate the mental construct with the real 3D object, cues are used to deduce 3D relations. In today's class, we shall go over the cues for depth perception. In general, there are static and dynamic depth cues. Dynamic cues are available when there is relative motion between objects and the observer. Static cues do not require relative motion. The cues can also be divided into monocular and binocular cues. Binocular cues are available when both eyes are looking, and monocular cues are available either one or two eyes are open. First, there are 5 commonly used static monocular depth cues. First, occlusion. An occluding surface is perceived as in front of the occluded surface. For example, we do not see, in this case, an irregular shape with an arc on the top right and straight lines on the bottom and the left. Instead, we see a blue circle occluding an orange square, or a blue circle occluded by an orange square. Occlusion is a cue commonly used in drawing. For example, in the Starry Night, we see this dark structure in the front because it occludes the clouds, the stars, and the hills. Second, size. Normally, larger retinal size signals nearer objects, but this requires some prior knowledge about how large an object normally is. For a normally sized tree, when it is nearer, it creates a larger retinal image than when it is farther away. However, as you have noticed, there is a problem. How could you distinguish a smaller but nearer tree from a larger but farther away tree? They both create the same retinal image. However, since from experience we know that objects do not usually grow or shrink their size, we tend to interpret a shrinking of retinal size as the result of the object moving closer. Let's look at this interesting video. It is an example of size constancy. It is called the Ames room illusion. Now you know how the fan effect is created with the Ames room. The question I posed is how to break the Ames room illusion. Third, the cue of linear perspective, which is that width between two parallel lines decreases as the distance increases. Depth is perceived when all lines converge to a vanishing point on the horizon. This is a powerful cue used in Western painting. You can easily find the vanishing points in these pictures. However, in Eastern art, linear perspective is not commonly used. Although one can also see depth structures with cues of size and base height and so on, the feel is very different with or without linear perspective. Linear perspective is often paired with other cues, such as size, base height, and density of texture elements. Linear perspective is powerful and it may take over other cues. Look at these interesting cartoons. They show the effect of linear perspective. The next cue is texture. Texture elements become more dense with distance. Texture elements become smaller with distance. Texture elements change shape with distance. This is known as foreshortening. By detecting these changes, we perceive depth, specifically to which direction a textured surface slants or bends. For example, when the textures are uniform and stochastically distributed, we see a vertical flat surface. When the textures become denser, smaller, and go through foreshortening, we perceive a slanted surface. The next static monocular cue is shading and shadowing. From experience, because natural light almost always comes from the above, we tend to perceive brighter regions as popping out and darker regions as caving in. The 4 pictures on the right show nicely what happens when highlight is added to line drawings, when shadow is added to line drawings, and when both are added to line drawings. Furthermore, distance between objects and their shadows suggests height of objects off the ground. For example, in this picture, the white squares look increasingly higher above the checkered ground. And the picture on the right, at the first glance, this man looks like he's hovering above the ground. A dynamic monocular depth cue is the motion parallax. For a moving observer, objects at different distances in the world have images with different retinal velocities and directions. Note, objects' actual moving speed and directions are the same. It is their retinal velocities that are different. In terms of retinal velocity, near objects appear to move faster than far objects. In terms of direction, objects that are nearer to you than your fixation point move in the opposite direction. Objects that are farther from you than your fixation point move in the same direction with you. Imagine you are sitting in a moving train. Near objects, such as trees next to the track, move past you, but far objects, such as the moon, moves with you. Next, try yourself. Can you list the depth cues in these pictures that help you to perceive 3D? When we observe with both eyes open, binocular depth cues are available. Remember, we have talked about the frontal eyes allow human observers to have larger regions of binocular vision. A functional advantage is to better perceive 3D. The binocular cues that we are introducing in this class are vergence and disparity. First, vergence. When the eyes move from fixating a distant object to a closer one, they rotate slightly toward each other. That is, they converge. This increases the angle of convergence between the two eyes, measured as the angle formed at the meeting of the two imaginary lines projecting from the pupil of each eye. When the eyes move from fixating a close object to a more distant one, they do the opposite, turning away from each other or diverging. The overall degree of vergence, referring to both convergence and divergence, can be estimated by feedback from the extraocular muscles that control the position of the two eyes. And as such, vergence is a cue for determining the absolute distance between the object currently being fixated and the observer. Vergence works for a small distance range between 0.5 to 4 meters. This is because when the target is very far, the eyes don't need to rotate much to fixate, and the rotation may be too small to be detected, or the cue is too weak. Second, binocular disparity refers to the positional differences between two retinal images generated at any instance by the two eyes. The brain uses this information to extract an estimate of the depth of an object or point. When we look at objects in the world, each eye sees from a slightly different angle. Objects that are farther or nearer than where we fixate are shifted horizontally in opposite directions in the two eyes, hence the term horizontal disparity. An object or feature, the green bowling pin, that is farther from fixation, the blue bowling pin, is projected outward, producing an uncrossed horizontal disparity between the two retinae. An object or feature, the white bowling pin, that is nearer with respect to the fixation, the blue bowling pin, is projected inward, or the left and right eye projections cross each other, producing a crossed horizontal disparity between the two retina. Therefore, a comparison of visual field locations of the same feature between the two eyes allows us to infer whether that feature is farther or nearer from where we are fixating. Note, this is relative depth. Putting together, vergence angle theta is inversely proportional to distance d. Vergence angle can provide information about absolute distance of the object. Horizontal disparity provides information about the relative distance, delta d, of an object being farther from or closer than a fixated object. horizontal disparity is directly proportional to delta D and PD, the pupillary distance, or distance between the two eyes, and it is inversely proportional to viewing distance. In normal viewing, there are commonly coexisting cues. How do observers combine them? The cue combination theory states that when cues coexist, our brain weighs each cue and combines them to form the final percept. The final percept is a weighted sum of the cues based on their goodness. Don't be intimidated by the equation. It is actually very simple. It means that each cue gets a weight as a coefficient. The weighted cues are added up to form the final percept. The weights were proportional with the goodness of the cues, or inversely proportional to the variance of the cues. If a cue is variable, then it has less weight. The idea is straightforward, but the realization and application can be much more complicated. Basically, the logic of perception is that we form percepts that must provide a coherent explanation for all the information contained within the visual scene. It avoids contradiction. It avoids interpretations of the world that are unlikely. When these logics are violated, we see impossible figures. Finally, let me pose a challenging question for you to think. Do you think monocular observers may function normally in the real world? What visual functions may be impaired, and what can be the compensatory strategies?